Okay, today we're going to be discussing Class 1 projectile motion problems. Let's recall, a Class 1 projectile motion problem looks something similar to this, a ball being kicked off a cliff horizontally. The main key here is to remember that we have quantities delta x, which is sometimes referred to as the range of the projectile. We also have another main quantity here, delta y, which is known as the height. It's important to recognize that these are both vector quantities, so I'll draw them in as those vectors. Notice that it's kicked off horizontally, so that it has a v sub x initial. However, its v sub y initial indeed equals 0. This is characteristic of a Class 1 problem. V sub x can be drawn anywhere, and it's always drawn to the same size, because V sub x displays constant motion in this x direction. It should also be noted that gravity is always down. Since all of my vectors are down, I'm going to consider them to be positive. Since I can separate my y motion from my x motion, my data table will resemble that. V sub x will be located in the x data column along with delta x, the range. V sub y initial, V sub y final, the acceleration, and delta y are all going to be placed into the y column. Yet notice that time resides here underneath both. It's going to take the projectile the same amount of time to make it to the ground. Characteristic Class 1 problem, Vy initial equals 0. Our acceleration in these problems, 90% of the time we're here on Earth using g. And time is our connector. Time is the bridge to take y data and solve for x, or vice versa, x data and solve for y. Here's a problem. A ball is kicked horizontally off a 72-meter high cliff. It leaves the edge of the cliff with a velocity of 43 meters per second. How far from the base of the cliff does the ball land? Let's move that to the side so we have some room to work. And let's build our data table. Here it is. We can begin inputting data. V sub y, again, horizontally off the edge of the cliff, V sub y is 0. We're here on Earth. The assumption is made. We'll assume that to be g. Notice Vy final is not asked for, nor is it told to us, so we will include that as data that is not asked for. Delta y is the height of the cliff. V sub x is 43 meters per second. The key to all of these problems is to solve for time. Let's see how we go about doing that. The lack of Vy final gives me the equation that I need to use. Delta y equals 1/2 gt squared plus Vy initial t. Congratulations, Vy initial goes to 0. Again, characteristic of a Class 1 problem. We're really just solving for the amount of time that it takes a ball to fall that distance. A little quick algebra here, and we can solve for time. Once we take the square root of this, we end up with, plugging our numbers in, we'll end up getting a value here. The value we get for time works out to be 3.83 seconds. Make sure you include your units. Now that I have the time that it takes to fall, I can now work on my range, how far it went. Start with the equation v sub x equals delta x divided by t. I don't need a big equation here because constant velocity. Do I know v sub x? Yes. Do I know time? Yes. I can solve for delta x. Little quick algebra, v sub x times t. We'll solve for my delta x. And I end up getting 164 meters, well, 0.7 meters, as my final answer for this particular problem. This is very characteristic as to how we solve projectile motion problems, but in particular a class 1 problem.